Welcome to video 19 on the TTB course. This video is from part 4 of the course. In part 4, we consider techniques for monitoring TT systems. In this video, we consider techniques for monitoring task execution sequences in a TT system. The material in this video is based on Chapter 19 in the ERES2 book. If you have not yet read Chapter 19, I suggest you stop the video now, read the book chapter, and come back and watch the video again. So let's begin with a review. As we've discussed, one key reason for choosing a TT architecture is that the resulting platform will have deterministic behavior. We can therefore model key characteristics such as the maximum CPU load, the response time and levels of task jitter. We explored these matters in part 3 of this course. This type of model is necessarily based on various assumptions, including the fact that we have operational peripherals on each processor, that we can transfer data between tasks on the same processor without corruption, and we can transfer data between processors without corruption. We explored techniques for testing these assumptions in part 2 of this course. Our models also assume that all processors in our platform are operating correctly. We are running the correct processor software on each processor. We have an operational scheduler on each processor. We know the worst case and probably best case execution times of all tasks on each processor. We know the execution sequence of tasks in each mode on each processor. If we fail to meet any of these assumptions at runtime, our models may not be valid, and we cannot be sure how the platform will behave in the field. We therefore need to incorporate mechanisms in our platform that will allow us to test these assumptions at runtime, and we need to consider what we will do if the platform does not pass one or more of these tests. In this video, our focus is on checking the execution sequence of tasks in each mode on each processor. Let's consider a simple example. Suppose the top of this slide represents the expected task sequence for our system. We've considered techniques that would allow us to determine if, for example, task A overruns or task B underruns. What we've not yet determined is how we could work out or identify situations in which, for example, the task sequence was represented by the second line on this slide. That is, task A, B, C, and D don't run. Obviously, A, B, C, and D don't exceed their worst-case execution time under these circumstances, and using the mechanisms that we've explored so far, we couldn't actually determine that these tasks haven't run. Similarly, we couldn't determine that the tasks have run in an incorrect sequence. For example, that's shown in line 3 on this display. So rather than A, B, C, D running, we get A, A, C, D. Similarly, we couldn't determine if the tasks run in the reverse order as shown at the bottom line on this example, so DCBA. We wouldn't necessarily pick up any of these discrepancies at runtime using the mechanisms that we've considered so far in this course. Does this matter? Well, it does matter, because this scenario can arise in real systems. For example, a task might be modified in an attempt to implement a reset-free mode change. This can have unexpected side effects. These may be either transient or permanent. It's possible that EMI will disrupt the scheduler or task array. It's possible that an accidental, incorrect code update will be performed. It's possible that a malicious attempt will be made to change the system behavior, for example by introducing a virus to the system. Some of these events may seem unlikely. Is it impossible that they could occur, or simply unlikely? could one of these events result in platform damage? If one of these events could occur and we have no other way of detecting them, then we need to consider mechanisms for detecting and handling this situation. Fortunately, this is very easy to do in a TT design. One simple question you have to ask yourself in these circumstances is, if you choose not to implement such a simple solution, one day you may have to explain in court why you made this decision. Let's look at this from another perspective. Designers of reliable embedded systems inevitably spend a lot of time considering three questions. What can possibly go wrong with this system? If problem X occurs, how can we detect that it has occurred? If problem X occurs, how can we best handle this situation? Despite such efforts, we don't really want to detect and handle problem X at all. What we really want to do is to detect that problem X is about to occur and react in a way that we can reduce the risk of reliability and particularly of safety consequences if problem X does occur. So we really want to perform predictive monitoring. Predictive monitoring is common in various branches of engineering. For example, we might use vibration measurements to detect that bearings are wearing out in a piece of machinery and call an operator to perform preventative maintenance at a convenient time, for example overnight when the plant wouldn't otherwise be used, thereby avoiding the need for an emergency shutdown when the system fails completely. When we monitor task execution sequences in a TT system, we are performing a form of predictive monitoring because we can determine in advance that a system is about to perform an erroneous action, in this case by running the wrong task. We can then alter the system behavior before the task is actually executed. This approach proves to be extremely powerful, and yet it's very easy to implement using what we refer to in this course as a predictor mechanism. Appropriate use of a predictor mechanism can prevent a system from taking actions at the wrong time, such as deploying an airbag in a passenger car erroneously, or raising the undercarriage on an aircraft. Without such a mechanism, we can often only react to such events after they have occurred. So let's look at the implementation of a predictor mechanism. As we'll see, this is really very straightforward. This slide summarizes the implementation of a predictor mechanism. In the bottom right, we have a representation of the scheduler architecture that we've used since the beginning of this course. So we have the scheduler ISR incrementing the tick counts. We have the dispatcher within function main that's releasing the tasks. We know from previous discussions that the representation of the tasks in the task array will be translated using what is a dynamic scheduler, will be translated into a series of task releases. We expect that these task releases will match the tick list shown at the top of this slide. So this is the expected task releases. What we will do is we will retain and use our scheduler exactly as before, but we'll add a second list to our system. So we'll add a tick list to the system. And before we release each task in the dispatcher, we'll check using the predictor mechanism against a tick list stored in memory. So before we release task B here, we'll double check against the list to make sure that B is supposed to be released at this time. The same for all tasks in the tick list. Either if the tasks that are to be released by the scheduler match the tick list, we just carry on and there's no great impact on the system operation. If we find there's a mismatch between the tasks in the tick list and the task that's about to be released by the scheduler, we will typically implement a fail-safe behavior, because it's difficult to know what else we can do in these circumstances. We can translate this into a small amount of code. So what we do here, this is part of the scheduler code that will probably be fairly familiar to you by now. So we've determined here that a particular task with this task ID is due to run. The first thing we do before we start the monitor, before we release the task, is that we check the task sequence using the predictor mechanism. You can find the full code for this in TTRD2 19A, which you can download from our website. So the full code for this example is in TTRD2 19A. So that's all we do. We have one call to check that the task sequence we're about to release is correct. This is what the task sequence representation will look like, the TSR. So this is our tick list in memory, which we refer to here as a task sequence representation. So this simply includes a list for each operating mode. We have a tick list that lays out which tasks will be released in each tick. So in this case, we have the task sequences shown here. We'll come back to why there are no tasks listed for tick 0 to tick 9 in the next few slides. So this system starts monitoring at tick 10 and goes on from that point. This kind of tick list you don't have to create manually. This kind of tick list is typically produced using a dry scheduler. And this tick list was produced using the dry scheduler that's implemented in TTRD2 A08A. That's the TTRD, the time-triggered reference design that's described in Appendix A8. So it's in Appendix 8 in the TTRD book. You'll find information about this example. And you can again download this example from our website. As you would expect, we will need to perform BISTs and POSTs, built-in self-tests and power-on self-tests on our predictor unit. So at startup, we would expect, having performed low-level CPU checks and tested both the internal watchdog timer and the scheduler, we would expect to test the predictor unit. We're also expecting to test the predictor unit periodically during the platform operation, in most cases. We'll assume that, as with the internal watchdog timer and the monitor unit, any such BISTs will be carried out by means of a same mode reset, unless another solution is found to be a better match for a particular platform. We've looked at this table before. This table is intended to form the basis of a discussion if you're considering how frequently you need to test the various mechanisms in your system. So this, the DTI, or the test interval used to test the various components in your system, is likely to vary with your choice of platform. We're going to say more about some of the platforms that are listed in this table in video 21. When we're working with a predictor unit, we also need to consider what's known as the TSIP. This is the task sequence initialization period. To understand why we need to consider the TCIP, please consider this set of synchronous signals. So this is a set of sine waves. The sine waves have different frequencies, but the signals are all in phase. There's no phase difference between the different signals. All of the signals begin at t equals 0. Similar questions can be asked about task sets. Are they in phase? The question is answered by considering whether there is any offset or initial delay for any tasks in the task set. So for example, in the first line on this video, the first line on this slide, this is a synchronous task set. All of the tasks begin executing in tick 0. So we have only two tasks, A and B. Tasks A and B both start executing in tick 0. Both tasks then run in every tick. The second set of tasks is similar but not quite the same. In the second set of tasks, we have A running as before in every tick with 0 offset or 0 initial delay. This task runs for the first time in tick 0 in the schedule. B, we'll assume, also runs every tick, but there's a delay, an offset, before task B begins executing. So task B runs for the first time in tick 2 and then runs from that point onwards. So this is a synchronous task set. This is an asynchronous task set. In practical systems, synchronous task sets are uncommon because in a synchronous task set, all of the tasks will be released for the first time in tick 0, and the sum of the execution time of all the tasks is likely to exceed the tick interval in tick 0 and in later ticks at the start of each hyperperiod in a synchronous design. Asynchronous task sets are much more common. When a set of asynchronous periodic tasks runs, there may be an initial period during which the task sequence is not the same as the task sequence when the system is in a steady state. We refer to this initial period as the task sequence initialization period. So in this task set that we looked at previously, the steady state is represented by the situation from tick 2 onwards. So the steady state task sequence that will be repeated forever if the system doesn't change mode and shut down is AB, AB, AB. And we could monitor that task sequence quite easily, of course, while the system is executing. But if we start monitoring that task sequence immediately the task schedule is released, then clearly at the start of the task schedule we're going to see AA. So this doesn't match our steady state task sequence, and if we were running a predictor unit, we would immediately think that something was wrong with the system. So when we're working with an asynchronous set of periodic tasks, we have to consider the task sequence initialization period. Do we need to consider the task sequence initialization period? If the maximum task offset is greater than or equal to the minimum task period, then the TSIP must be considered in your monitoring system. So the maximum task offset is the maximum offset measured in ticks of all the tasks in the set. The minimum task period is the minimum period, again measured in ticks, of the tasks in the task set. So if this maximum task offset is greater than or equal to the minimum task period, then the TSIP must be considered. Let's look at an example. Here's a set of tasks. Task X has a period of 1 tick and an offset of 0 ticks. Task Y has a period of 2 ticks and an offset of 1 tick. Task Z has a period of 3 ticks and an offset of 2 ticks. In other words, there's an initial delay of 0 before task X runs for the first time. So task X will run in tick 0. There's an initial delay of 1 before task Y will run for the first time. So task Y will run for the first time in tick 1. There's an initial delay of 2 ticks before task Z will run. Task Z will run for the first time in tick interval 2. In this case, the maximum offset is 2 ticks and the minimum period is 1 tick. We therefore need to consider the TSIP. After the TSIP, the steady-state task execution sequence begins in the tick interval in which the task with the largest offset runs for the first time. Task Z has the largest offset, which is 2 ticks, and this task is released for the first time after tick 2. So in tick interval 2, we'll begin the steady-state task sequence. In many platforms, we start monitoring the task execution sequences after the TSIP is complete. That is, we ignore the TSIP when we are monitoring the system activity. In order to start monitoring at the right time, we clearly need to know the length of the TSIP. The most useful measure of length in these circumstances is usually a count of the task releases in the TSIP. So we usually wish to know how many task releases will occur before we reach the steady state situation, so that we can disregard these samples during the monitoring process. Please remember that you have to consider the TSIP when your system starts up and any time that your system changes mode. So when you change into a given mode, you need to know how long the TSIP is for the task sets in that particular mode. Let's go back to the example that we looked at a few minutes ago. So we've said that the task sequence initialization period is 2 ticks, the first 2 ticks here. So the steady state begins in this example when task Z runs for the first time. Task Z runs for the first time in tick interval 2. So this is the beginning of the steady state process. Before we get to tick interval 2, we have 3 task releases. So there are 3 tasks released during the TSIP. In larger systems, we can't usually do this by hand, or it's rather tedious to calculate the length of the TSIP by hand. We usually need a dry scheduler to calculate the TSIP length. If you have a look at the ERAS2 book in Appendix 8, you'll see a suitable dry scheduler that can be used to determine the TSIP. Here's a slightly larger example. So we have a set of tasks here, task A to task G. Tasks have various offsets from 0 up to 25. So we know that in this case G has the largest offset, 25 ticks. So we know that the task sequence, the steady state task sequence, begins in tick 25. The length of the TSIP we can calculate, again manually here, as follows. By working out how many releases of the tasks will occur before we get to tick 25 when G runs for the first time. They're summed up here, and the total will be 70 task releases in the TSIP. Again, as noted in the previous slide, you can use a dry scheduler to perform these calculations automatically. You don't always need to do them by hand. The information about the expected task releases in a predictor unit is called the task sequence representation, or TSR. When we use an internal predictor unit, we store the TSR in an array in internal memory. When we are working with a warrantor unit, we usually store the TSR in this unit. We discussed this in video 20. When we are working with a duplicator platform, we have 2 processors. Each will usually contain the TSR for the other processor. That is, microcontroller A will store the TSR for microcontroller B and vice versa. Each processor can then check the task sequences on the other processor during the system operation. We'll discuss this option in video 21, and you can find out more in Appendix 3 in the ERES2 book. So the area in which we store the TSR will vary depending on the particular system platform that we are implementing. For the simplest designs that we're considering initially in this course, then we will use an internal predictor, and we will store the TSR in an array in internal memory in the processor that the scheduler is running on. Overall, we've discussed previously in this course that as the safety integrity level of a system increases, we would expect to see the level of diversity also increase. So we'd expect to see a rough relationship that as the system becomes more safety critical, as safety becomes more important, we'd have a higher level of diversity in the design. You can view a predictor unit as a mechanism for incorporating additional diversity in your system design. So what we have with a predictor unit is we have two representations of the task schedule. One representation is given by the scheduler array and is calculated dynamically, and the task releases are calculated dynamically at runtime by the scheduler using information in the scheduler array. The second representation of the task schedule is given by the task sequence representation, a separate simple representation of the expected task releases for the system. So we have diversity here, two different representations of the expected task release schedule, and that gives us increased confidence that we'll be able to determine if something goes wrong with the task schedule at runtime. That brings us to the end of this video. Please read Chapter 20 in the ERES2 book before you continue with the course. Thank you for watching.